Hi, Kent. Can you hear me okay?
I can, Mohan. How are you?
Great. So this is the second session today. We're going to be talking about DB2 11.5, PureScale and implementation principles. This is a glimpse of what we have as a crash course. We do have a crash course for this one for about 3.5 hours. And that is a paid subscription, by the way. It's $100 per subscription, unlimited access, and the participant can get to ask questions via email or can join our weekend class, the session what we have for about 90 minutes for the question answer. So
We're
they can
calling those
join
doubt sessions,
doubt
right? That's
session.
what we're
Yeah,
calling them. Yep.
yeah, doubt session, and we will address as much as possible. Kent, do we have any disclaimers?
We do. You know, the internet's full of information, right, from various people, a lot of really smart people. But Mohan and I, for the database channel, we're going to do our very best to present information that is specific to areas that you've pointed out to us that you're interested in, and the materials that we present. We've either tested ourselves or we're very, very confident that that what we recommend to you is a best practice or the way to do things. Obviously, your environment is different, might be different than ours, so we can't guarantee that everything that you implement that we recommend will work exactly like we say, because it's just too many variations there. But we are going to do our very best to provide you accurate information that is solid and you can implement it. So that's our promise to you, that we won't speculate on anything, and we'll give you the very best information we can.
Thanks, Kent. The learning objectives for this session is about introduction to PureScale, internals of PureScale, installation, management of DB2 cluster, backup and recovery, monitoring and troubleshooting, and the new features within 11.5. We go up to 11.5.6 in the crash course, right? This is a glimpse of what you see in the paid version. Let's take a look.
And today, you and I, we've built from scratch up to 11 clusters to date.
Right. Yeah. From 9.8 to 11.5.
That's correct.
From the day one of PureScale. Introduction to PureScale. So what is the purpose? What is the use of a PureScale cluster? It is extreme capacity. You can add as many compute resources as you want. There is a limit, right, from a member's standpoint, but we'll talk about it. But it is extreme. And continuous availability, no single point of failure. So we have dual capabilities in every single component of the database engine. So that's the reason there'll not be any single point of failure, which can lead to a database crash or unavailability of your application. And application transparency, that's very important in a cluster. So no change required in the application code to make it work for PureScale. If it is working for a single node database, then it will work as well for a PureScale. So there is no point of code change, right? A load balancing logic is built within the DB2 engine. You don't really have to worry about how are we going to distribute the load across multiple members in the database cluster. And if your client is very specific and then you want to make use of the additional load balancing capabilities, we have a lot of them, which there are features available within the DB2 dsdriver.cfg file. I think we're going to talk about the DB2 dsdriver.cfg alone in about 20-minute session, because that configuration is very important for you to know, because it's going to be giving you multiple other features about how exactly you can load balance it, how exactly you can enable the enable alternate server definitions, and how are you going to capture the exceptions, right? And then how do you enable the ACR, automatic client readout feature? How do you enable the max ACR retries? So a lot of things, along with the keep alive timeouts and all that, can be done within DB2 dsdriver.cfg. So we're going to set up one more session to go over in detail and how you can make use of it. And you can also use big F5 or big IP, which is also called F5, to load balance your connection in a round robin fashion. Let's look at the architecture from a 1,000 feet overview. So that's about a client connecting to the database. It will see a single DB view. It is not going to see all the members which are present in the cluster. But for the client, it is a single database. It's nothing different than a standalone database, which is ESE, right? We can have multiple members, right, for availability purposes and also the performance improvement purpose, right? So for example, member 0 to 127. So that means we can have maximum of 128 members in the cluster. And then we will have primary CF, the cluster caching facility, and a secondary cluster caching facility. So these two will act as a brain for the entire cluster. And these are interconnected via RoCE interface, which is RDMA, Remote Direct Memory Access Protocol. It is built to improve the performance, to communicate via between the servers or between the CFs pretty effectively, right? It can support multiple interconnects. One is RDMA over InfiniBand. That was the earlier version of RDMA support, but now from 11.5 or even 10.5, we also support the RoCE, right? So that's a RDMA protocol over converged Ethernet network, and also TCP/IP protocol over Ethernet. Those are also supported as part of RDMA protocol support, or the interconnect support. Let's look at what a member is, or what a CF is. So because these two are very important concepts within the pureScale, right? And as you see here, the log streams is a mapping between the number of members what you have and the number of log stream you're going to be getting. So if you have 3 members, you will see 3 log streams: log 0, log 1, log 2. And if you have up to 127, 0 to 127, you will have 128 log streams, log 0 to log 128. So log streams are not are written by the member, by each member. They're not overwritten by the member, but these are reusable. They are usable by other members. For example, if member 0 wants to read from member 1, yes, it can read, because these are all sitting in the same shared file system. Okay, so that's the reason. Let's take a look at the member. So what is a member? So member is a DB2 core processing engine within a pureScale, similar to what a single node database is. There's no difference with respect to the number of system controller processes, watchdog process, your buffer pools, lock list, and database heap, and log buffers and all that, right? But you see a little bit of differences. One is about the DB2 system controller process. By default, when you run on a single node, you have one DB2 system controller process which is going to be running. But when you see it on pureScale, you will see one which is active, and the other three will be in idle state. So those 3 are built for a purpose called restart light. If something happens to another node, then if you want to fail over to or host that particular node as a guest host or guest node, then the system controller process, which is idle in nature, that will take over and then serve the purpose. And because the reason why it is pre-allocated is basically not to have a resource contention when there is a failover. So basically, it's going to DB2 will allocate a little bit of memory, a little bit of CPU cycles for that particular system controller process, so that it can take over as quickly as possible and as effectively as possible. So that's the reason. All right. So let's look at other DB2 processes which you see, right? DB2 construct event. And these are all engine dispatchable units. You will see additional to what you see for a single node database. DB2 construct event, basically it reads the state of a CF link from 2 different files. One is the PGRP file, and the other one is the isOnline file. It keeps checking about the CF links. Is it working, functioning okay or not? Then we do have other EDUs such as DB2 LLM1, LLM2. These are the one which are global lock managers. So in pureScale, we have a local lock manager, which is on every single member, and a global lock manager, which is sitting on CF, right? So that's where the additional engine dispatchable units comes into play. We're going to be talking in detail about these in our subscription-based crash course, okay? And what is the difference in terms of logging, right? As we talked about it, each member will log to its own log stream, and these can be read by the member but cannot be written by the member, okay? So it's only reading. And we do have a deadlock detector, and also GLock, that is the coordinated deadlock information between multiple members. That is like a global lock manager for the deadlock. So that is one you see as a difference between the two. But DB2 page cleaner, prefetchers, and everything would remain the same between a single node and the pureScale member. Look, there is a difference, right? So let's look at one of the concepts called catalog node, which is present in DPF. There is no catalog node in pureScale. It is every node, which is the member, will be a member which can process the data. There is nothing like DPF where catalog node will host all the metadata. It is here every single database can read, can write, because the data which is sitting here is a shared. So MPP is a shared nothing architecture, whereas pureScale is shared disk architecture, right? So we will talk a little bit on the differences between these. ESC, MPP, that is DPF, are also called massively parallel processing, and pureScale in about a couple of minutes. What is a CF? So CF is a brain for this entire cluster. It facilitates the data sharing and concurrency control between members, right? And also it works as a data caching facility for the entire system. It consists of three components. One is the group buffer pool, or global buffer pool you can call, but group buffer pool is the one which is mainly called as, and global lock manager, and shared communication area network, shared communication area memory. So local lock manager, each member will have the local lock, right? The lock list, which is present on each member, will serve as a LLM, and the global lock manager will coordinate each LLM and GLM. And the shared communication area contains the cluster-wide or database-wide information about the tables, indexes, table spaces, and catalog. So kind of metadata information which will be kept on shared between the two, between the members and CF. Let's look at what happens when there is a read happening, right, in a pureScale cluster. Before that, can we discuss about what the difference between ESC, a DPF, and a pureScale?
Yeah. So as you pointed out earlier, right, pureScale is really a series of instances deployed on individual servers that really the only thing they share is a file system. So you can stop member one, start member one back up, and the other members will process normally. They'll take over the workload from the member you stopped. And then when the member comes back, that workload will get moved back to that member. And so they share nothing but the file systems. DPF, if you just go by what it stands for, database partition facility, you're talking about deploying in a key state data across multiple nodes. So you're spreading your data out across multiple nodes. In the case of DB2 pureScale, you could still just have one table, right? Just one table, one partition, and all the members are reading that and writing to that one table and that one partition. Of course, in ESE, sometimes referred to as LUW, you have one standalone database. There's no group buffer pool in a DPF environment. There's no group buffer pool in a LUW environment because they don't pass information back and forth to one another. In the case of DPF, you determine the number of partitions that you're going to use. They're basically called nodes and partitions. In the case of pureScale, we call them members, right?
Correct.
So we'd have separate members. And there's an awful lot of other differences, I'm sure, between pureScale and DPF, Mohan. So what would you say are the differences?
Right, thanks, Kent. So let's look at number of log streams. So in a single node ESC, we will have only one log stream, node 000, right? And in case of DPF, it's the number of nodes you have. The number of nodes you have, it's going to be log streams are written, and those are going to be written to its own log file system. You can
Yep.
dedicatedly create the log files, a file system dedicatedly for each of the log, each of the node. In DPF, it's going to be same. Each member will host the log stream, but those are going to be sitting in a shared file system. That's the difference between DPF and pureScale.
So
Then,
I got a question for you.
sure.
In the pureScale world, right? In the pureScale world, so you have an LSN, right?
Mhm.
Don't members of a pureScale have the same LSN? How does pureScale know the sequence of applying logs for replay across multiple members if the LSN could be the same for 3 members? Wouldn't it like have collisions? How does it manage that?
LSN can be same and can be different. So one thing is, and also it can have the same LSN number. Most likely no, because what will eventually happen, the LSN sync will happen every single time when you perform a data change. I mean, the table change, for example, if you create a table, then the LSN for that member where you're creating the table will take the higher precedence. The number will goes up there, and then it will automatically sync the LSN number across all the members. So that LSN number will go up from any other LSN present in the cluster. And we do have a complete session on the LSN, how the log is going to be syncing between each log stream, and how the LSN is going to be determined by the illustration of the example. So yeah, so we did present in IDUG. We will have a detailed session here as well. That's going to be for about 30 minutes, just about how logs are going to be different than a single node.
And the whole restart light, right? A member can take over the transaction execution of another member, right?
Correct.
So that member fails, and that's what we were discussing earlier. Whereas in a DPF environment, you could actually have a partition become unavailable, right? Because the node is down, right?
Correct. If the node is down, the problem is with the DPF, if the node is down, you're completely down, even though the data is only 10% or 5% of the entire data set what you have, but the cluster will become inaccessible. You can read, it is no problem in connecting, but when you try reading a table, it won't. But in pureScale is not the case. So in pureScale, even on one member is down, you will still get the data back. It's no problem, right? And that's why in DPF, what we do is we'll build a standby for each group of members. So a group of nodes we call. Say, let's say if I have a 10 node, 10 data nodes, and then one admin node or catalog node, then we tend to build 2 standbys. One is for first 5 plus 1 admin node. So 6 will fail over to one, then the next 5 will fail to the other. So everything is built via TSA system, Twilio system automation, multiple platform. So that's the one we are using even in DPF as well. So that's the reason we will have failover capability. As and when the failover is complete, then your data will be read.
And would that be considered like, let's say if you have 1 gig of data, then you'd have 2 gig, right? You'd have a gig primary, and then you'd have a gig for the failover. In the case of pureScale, right, you have GPFS is handling all of that under the covers for you, but you technically only have 1 file system, right? I mean, or n number of file systems, and they're all seen by the members at the same time, correct?
Exactly.
Yeah.
And in the case of a pureScale, when the restart light happens, it only holds the in-flight transactions. For example, any transaction which is not committed yet, those are the ones which will go on the guest host and then perform the commit or a rollback. So that is just about that. It is not going to be holding anything which is previous because already committed. So it's only worry about in-flight transactions to commit or roll back those transactions. So as and when it's complete, it will release all the PLOCs from that member, and any new request coming in doesn't see that member. So any new request coming, will not be serviced on the restart light member or the host, guest host. Everything will be on the members which are active.
Yeah. So I'm sorry, I kind of interrupted you on that little on the discussion on the locking. Real quick, what command would you execute to determine where workload's running? If you wanted to see the status of the cluster, what would you run?
State of the cluster is basically DB2 instance -list will tell you the status of the complete cluster to say where each host is running or each member is running. Is it running on his local or running on a guest host?
And that's a real important point to make about pureScale, right? I mean, while it's a cluster technology, IBM implementation of this technology leverages the DB2 DBA commands that you're familiar with, even in LUW, right? DB2 list applications works, right?
Yeah.
That command works. That you may add the parameter global if you want to see it across the entire cluster.
Correct.
But the basic command still works, right? Even in a pureScale cluster. So you don't have to like relearn everything. You just need to understand the difference in cluster technology versus a standalone instance technology.
Exactly.
Whereas DPF really is, it really is an implementation in and of itself. There's a lot of knowledge you need, a lot of understanding you need to properly best practice implement a DPF environment.
Right, and also the workload specific. For example, pureScale is primarily for OLTP transactions where you want to scale up your workload in an OLTP environment, and for DPF or MPP, it's basically for reporting or OLAP kind of a workload. Cool. So let's look at a little bit of examples how DB2 pureScale does the work when it tries to do a read or a write operation, how the other member looks at it from the data standpoint. So that will give a clarity around how pureScale works in structure, right? That will give a benefit. So let's look at, I have two members, member 0 and member 1. I'm doing a select from employee table where employee number equals 100. The first scenario, the first command, the statement went to the database member 0. It checks it. Oh, no, this page doesn't exist in the buffer pool. It will send a request to global buffer pool or group buffer pool here. It will say, oh, I do want this page and I'm interested. In that case, it sends a request called read and register request. So we have multiple commands which will each member sends it to CF. These are called the read register commands or read write commands. So here it's going to be sending read and register command because I want to register my request as a request to be made to get the page. So what it does is it will register in our registry. It says P1, page 1 is interested by member 0. Then it will register and then sends back the request saying, yep, I do have your registration done. Go and read the data from the storage. It reads it from the storage because that data is not present in the GBP at the moment. So it reads it and then it will pull in the local buffer pool and sends the data back to the application. Even though it has to perform multiple steps before sending the data back to the application, like all this is happening via RDMA, remote direct memory access. It is pretty quicker in response. It's in nanoseconds. So that's the reason where you don't really see extreme latency between multiple systems, multiple requests going across multiple systems. Now let's look at what will happen. So this is just about example. I mean, whatever it is happening here, we have illustrated to give a better better readability feature. So let's look at scenario 2. What if I want to do an update on the same data page, right? So now I'm sending an update employee, set phone number equals the new phone number where employee number is equal to 100. It sent the request in, and then I do have the page already in the buffer pool this time because it read it last time from the storage, right? It is already present. It says, okay, I do see it. It sends the data back again stating, yep, it is done. Look, even though it sent the request back to the application stating the commit is complete, I mean, the update is complete, it will eventually do multiple other steps before it commits to the data. So one is the fourth. So it has to send the request to GBP stating, I'm interested to register and write. So it basically sends, it's a request called write and register. GBP states, okay, you made a change to P1. This basically extract the new page which is present in the LBP into GBP and sends the result back. And that point, the commit will happen. As in when the commit sends back from the application, commit will be sent to the local member or local buffer pool, and that will be sending a request to the GBP, and GBP will do a cast out. So there is a cast out operation within within pureScale, where as in when you commit, it will commit the data which is present in a GBP to the disk, right? So if you see overall, the data copy for the page P1 did not go across the storage this time. It read it from the local buffer pool of a member to a GBP, right? Let's look at one more scenario where member one trying to read the same page. Okay, what will happen in that case, right? So if you see here, member one is trying to read the same page based on the SQL statement, select star from employee, where employee number is equal to 100. And it's trying to read the same page, right? It sent the request to the member. So local buffer pool sent that request to GBP. Remember, as and when the read request needs to be made, it has to send a request called read and register request. So it sent a read and register request to GBP. That GBP registered here to say, okay, member one is interested in page one. Okay, then it sends back the page. It sends the recent page, which is currently modified by member zero. So look at it. Member one doesn't have to go to member zero to get the data. It got it directly from GBP, because GBP is holding the recent copy of the page. That's the reason always this is the multi-layer caching, where it doesn't have to go to the storage. It will directly go to GBP and get it. GBP sent the data back in, and that will be sent back to the application. Let's look at one more scenario where member one is trying to write the same page or modify the same page. What will happen in this case? Multiple other things will happen in this scenario. So let's take a look. Application sends an update request, which is basically update employee email address to be updated for the same employee number 100. Then it sent a request. The page P1 is already present, by the way, right? From the previous example, it read the new page. That was a recent page of the data which is present in member zero, and it sends it back saying, yeah, so return the update SQL successfully, because it found that particular page in the local buffer pool. But be aware, the page which is now modified is a dirty page which is sitting in local buffer pool, and this will be sent basically as a forced commit signal to copy the LBP data to GBP. So what will happen is it modified the data, it sends a request back here to say, okay, I do have a write and register request to be made, because I'm making a modification to page P1. And that will be sent via a signal called forced commit. And it comes here, and then the number 5 is, because member 0 is holding a copy of page 1, but it is not a recent one. So what CF does, it sends a signal to member 0 stating the page what you're holding is invalid. So I'm invalidating your page. It is not going to do anything. It just sends an invalidation signal, so that if any request coming into member 0 later, it knows that P1 is not recent, it will go back and read from GBP again. So once the invalidation is complete, it will send the data back again to member 1 to saying the replay is complete and SQL can be committed. At that point, application will send a commit, and commit will be sent back as a application is committed to the global buffer pool, and that's in this, that a forced commit in action that has written the data to the disk. So this is the overall transaction activity when a select happens or an update happens to the table. So again, the important element here is about the access to the storage. If you look at from the last 3 scenarios, it did not even touch the storage. It was just the page was floating between the members and the GBP. Right, Kent? What do you think? What do you think about this architecture?
I think it's a wonderful architecture. You and I see it in action every single solitary moment of every single solitary day, and it's a very strong I/O reduction, right?
Yeah.
you know, and again, we're not going over it now because it's just an introductory, but there are metrics that show you the GBP hits and the GBP misses, so you can kind of get an idea of the IO avoidance that your system is able to gain by the number of GBP hits that occur during the day, right?
Exactly.
So, yep.
And we do provide the guidance around how to eliminate the page reclaims and all that in our crash course, right?
Yep. Yep. And what can you briefly tell us what a reclaim is? Would you
A
do
page
that?
reclaim, yeah, certainly. So a page reclaim is basically going to happen when a member, let's say, take an example here, a member 0, it did read and then trying to write. It did not release the page level lock, but the member 1 wanting the same page at the same time, then the page member 1 sends a signal to GBP stating, I need that page to be modified. In that case, GBP will send a request to member 0 to say, can you release it early? So that early is nothing but a page reclaim. That is an expensive operation because before GBP confirms the member 1 to make the change to the page, it has to get the confirmation from member 0. So that's where the acknowledgement will have to, will play a critical role that will impact your performance. So we're going to talk about how do you eliminate those performance impactful operations.
Yeah. Now, in our environment, Mohan, that you and I work in, where we've like I said early in the broadcast here in the conversation, we've created 11 clusters, and they run different kinds of workloads, right? But we run those clusters. We don't affinitize, do we? We
No.
run the clusters in workload finds resources, right? We let them float in the cluster, right?
Correct.
And have we seen any horrible consequences associated with that, or can we run the pureScale cluster in that manner?
Oh, we can certainly run in this manner what we're doing, but also we can also look at subsetting and all that, right? So based on the application design and availability requirement, when you try to host multiple applications on the same cluster, we can certainly go with the other approach, such as subsetting the members and using the db2 nodes db2 driver.cfg to improve the connectivity from each client to the database server.
Yeah, and there are other technologies like RAC, Oracle
Yeah.
RAC, for example, where batch workloads in many cases need to be affinitized. It has to do with the chattiness of the global lock manager implementation in Oracle versus the implementation that we see here in pureScale for IBM. And the reason for the success of pureScale is one of the main reasons, not the only reason, but one of the main reasons is this is not new for IBM. They implemented a very similar technique with physical and logical locking in what they called the coupling facility, which was the data sharing implementation on the mainframe. So they didn't have to relearn how to write a global lock manager or how to handle registration of pages in a global buffer pool, because they had experience from the early 90s with data sharing implementation. And so they could leverage that same understanding of the architecture when they built pureScale.
Right. I think we want to cover a little bit on how the quizzes have been written in our database university. We do have a lot of quiz were prepared, and then a sample is here. Can we take a look at it, Ken?
Yeah. Wow.
Yeah. So just not about the questions and answers, right? To say which is the right answer. We also provide the right answer, why it is the right answer, why we eliminated the incorrect answer. So we have given, for each question, the answer is not a simple one-liner. So they get to see about at least 2 paragraphs to say why it is so and what's the reason behind it. That will be helpful for even interviews and understanding the concepts in general.
Yeah, and of course, on a slide that you just showed just a minute ago, when you were actually showing the pureScale architecture, you actually had a 127 member
Correct.
entry. So I would say the answer to this one is number 3, just because I saw that slide.
You're right. Absolutely right. 128. How many CFs one should be provisioning for a production cluster?
Well, again, you and I have built 11 of these, and I remember not too long ago, we purposely cycled a cluster in our environment because it had been up and running for over 160 days. So
Right.
these clusters are meant to be very highly available and redundant and very resilient to application failures and other conditions and issues. So I know it's not 0. 4 seems like a fairly interesting number. I'm confident it isn't 1, because that would mean there was only one of them, and there's no resilience. So I'm going to go with number 3 as being the right answer.
Cool. Yeah. Two CFs, right? Yes. Primary and standby.
Yep.
How many GBPs one can have in a production database in pureScale?
Well, this one is interesting to me because it required me to think really, really hard when I saw the question. I know it's not 1. Again, back to what we had said before. Very rarely is the answer 1 when you were talking about pureScale, right? Because it's a cluster technology, and you're trying to keep it highly available. So 1 is generally not going to be the right answer. I think 4 is interesting. I don't think it's 3, just because it's an odd number, and I'm not crazy about odd numbers when this kind of question pops up. So if I remember correctly, there are 2 CFs, and because there are 2 CFs in a production environment, there will be 1 active GBP, and there will be 1 standby GBP. And the CFs are communicating through dual links between each other, and the primary is transmitting these registered pages to the other CF. As a matter of fact, you can even see the gap, I believe, Mohan, right?
Oh, yeah.
We can actually see the gap, right?
Exactly.
And on a takeover, it's got to reprocess that before it makes that secondary active. It's got to get all the way caught up. It'll specify that it's in peer state. It'll actually tell you that it is. And it just reprocesses that gap, and then that particular CF becomes active. Now, that's not just for the GBP, but it's also for the lock list as well.
Correct.
But I'm going to say the right answer here is 2.
Right. You're right. So 1 on the primary and 1 on the standby. Just about to address, right, even though you can have multiple local buffer pools with different page sizes, 4K, 8K, 16K, 32K, you can have hundreds of them, but at the end, those will be transmitted to 1 GBP on primary and 1 GBP on the standby.
Yep.
What is the page size of GBP? Interesting, right?
Yeah, it is interesting. You know, if I had been working at IBM when they built the and wrote the technology for pureScale, I might would have picked number 2 on this list. 8K seems to be, you know, pretty good. The other thing too is in the Oracle world, right? In the Oracle world, they used to do, back in the old days, right? The system block size determined the page size for your Oracle system back in the old, you know, pre-version, I think version 10 or version 9, they came up with multiple sizes as well. But you would implement them based on the system size, right? And you could set the system size on the system wherever you deployed Oracle. In the case of the GBP, I believe 32 is too big. I think 16 is just wouldn't be a good choice. So I'm going to go with number 1, 4K.
Yeah, that's an awesome pick. That's the right answer. All right, I think this presentation would probably give a good glimpse at what they see in our subscription-based videos, right? Please feel free to contact us via email or contact us via Discord channel. I'm going to be sending the Discord channel in the in about a few days. And you can also try to contact us via the email address listed in the database university channel.
Yeah, PureScale for you and me is very important. We're evangelists for PureScale. We our organization that we work at has PureScale on the strategic list of products to implement. It is our relational database solution of choice as an organization. We've got a lot of time invested in it and a lot of energy invested in it. It's really important to us, isn't it, Mohan? It's
Oh yeah, certainly.
really
yeah.
high on our list, and so we really enjoy working with it, and it's proven to be very successful in our environment.
All right, thanks, Kent, and we'll see you again in the next video.
Great presentation, Mohan. I can't wait to see the next one.
Thank you. Take care.
Bye.
Bye-bye.